Hey everybody, this week for lab, we are going to have one pre-lab for both of our face-to-face and at-home labs. And you're only going to have one lab participation that you're going to submit, but it's going to have two parts. You're going to do part of the lab at home and part of the lab face-to-face with me in person. And so here I'm going to work through some background that we need for the pre-lab and the lab. We are going to be talking about simple harmonic motion and waves. So we're going to start to talk about waves by looking here at a computer simulation. This is one of the PHY simulations, and this one is for waves on a string. So this is the default that you see when you come here. And what we'll first see is a string, and at one end of the string it's connected to a wrench, the other end of the string is connected to a clamp, and I can wiggle this string up and down, and I can set up a wave pattern. We are going to be setting up wave patterns on a Slinky in lab this week. I'm going to make my system oscillate for me by clicking this button here, and I've got a little motor that's moving my string up and down. We see that there's a bunch of controls down here at the bottom. Damping is how much energy do you lose in your system. I have not much damping happening here, but I haven't said none. So the amplitude of my wave is going to be different over here at the end where we're oscillating with the motor versus the end over here. The amplitude is how high above this midpoint, x equals 0, is that trough or peak of the wave getting to. And so I've also increased the amplitude over here to 1 centimeter. And I'm going to, this is in slow motion, I'm going to stop this right here so that we can talk about our wave. Now there are a couple of pieces of terminology we can use to talk about waves. One of them is called the wavelength. The wavelength is the distance between consecutive peaks or troughs in a wave. And you can also describe the wavelength as the distance between where you start and where you end your repetitive pattern along the wave. So here I have my wave passing through 0. It reaches its maximum amplitude, it comes back through 0, a minimum amplitude, and then it comes back to 0 again. This is my repeating pattern for the wave. This is reminiscent of a sine wave, okay? If you remember back to trigonometry, this is reminiscent of a sine wave. So the wavelength would be the same between here where I start my cycle and where I end repeating my pattern. That would be one full wavelength. The wavelength is also the distance between the peak trough, or the peak of my wave here and the peak of the wave here. And I can even test that out by bringing in the ruler. I just click the ruler here. I can move it to see, it looks like it's about 4 centimeters between consecutive peaks in my wave. And then maybe about 4 centimeters, not quite, between consecutive troughs. It should be the same if we had no damping in our system. And then the distance between where I began my pattern, went up, back through 0, down, and then back to 0 again. That's also 4 centimeters. So the wavelength of this wave is turning out to be 4 centimeters, okay? And then we can also talk about the frequency. The frequency is listed here. The unit of frequency is hertz, H-E-R-T-Z, which we abbreviate as Hz. For any oscillatory motion, which we have here, the frequency is how often a periodic motion happens each second. So how many of these periodic oscillations per second? So it's a number per second. So that's an inverse second, and we just call it a hertz, okay? So you can use the frequency to describe the wave. The frequency is inversely proportional to the wavelength. So as your wavelength gets longer, your frequency gets smaller. As your frequency gets bigger, your wavelength gets shorter. So let's test that out here. Here we have our wavelength is about 4 centimeters, and we have a frequency of 1.5 hertz. Let's see what happens when we increase the frequency of our system. I'm going to increase it up to 3 and then play and see what happens. So if our frequency gets larger, our wavelength should get smaller. And I think it did. So we got a frequency up to 3 hertz. So I'm gonna stop it right there, okay? 3 hertz, and then increase the frequency. Our wavelength should get shorter. So if I come over here and test my wavelength, I do see that now it's somewhere around 2 centimeters. When I increase the frequency, my wavelength decreased, okay? So you can pack more of these repetitive cycles in the same length of string by increasing the frequency. That's what's happening here. So now we have a couple of more of these nodes and antinodes. So another way we can define the wave is by talking about the nodes and antinodes that we see. The node is when our wave, the shape of the wave pattern, passes through our equilibrium line here, x equals 0, okay? So we've got 1, 2, 3, 4, 5, 6, 7, 8 nodes. And the antinode is the peak amplitude away from our x equals 0 line. So if we had 1, 2, 3, 4, 5, 6, 7, 8 antinode or 8 nodes here, we are going to have 1, 2, 3, 4, 5, 6, 7 antinodes. And the antinode again is your peak amplitude away from that x equals 0 line, the equilibrium line down the middle. Okay, so let's see. You can decrease the number of nodes or antinodes then by reducing the frequency, because when you reduce the frequency, you end up with a longer wavelength. If we have a longer wavelength, we're not going to have as many nodes or antinodes on that same length of string. So let me move my frequency down to 1 hertz and see what happens. So now we're reducing our frequency. It's going to take a while. Right now what we're seeing is superposition of waves. Some of those waves are still interacting with each other until this string gets back to its base oscillation. Let me put it to the normal here. Okay, so now I have a wave with a frequency of 1 hertz. So let's see what happens here. I reduced the frequency, smaller frequency, which means I should have a longer wavelength. And this time we do. We have a longer wavelength. And in fact, the wavelength is the entire length of the string. We start here, we go down, back through the middle, up to a maximum amplitude, and back down again. So here I've got 1 full wavelength fitting into the whole length of my string. And in this case, I only have 1, 2, 3 nodes and 1, 2 antinodes. Now the frequency is also related to the energy that you pump into the system. Now, the more energy you put into the system, the higher the frequency. The less energy you put into the system, the lower the frequency. So if we have a very low frequency here of 0.5 hertz, we're not putting in as much energy to the system, okay? And then that also translates to our wave having a longer wavelength. We can also define the period of oscillation. The period is the time it takes for a periodic motion to complete 1 cycle. So the period is the inverse of the frequency, or the frequency is also the inverse of the period. So here we know the frequency. So the period of oscillation for this wave is going to be 1 divided by the frequency. If frequency is in units of hertz, which is an inverse second, if the period is equal to 1 over the frequency, we take 1 divided by an inverse second, we get back units of seconds. So the period is always going to be in units of seconds if we have our frequency in units of hertz.